Let me just show how to do on a Google instance here. Let me put, okay. You open a web browser, you just like go here, type Colab, and if you already log in on your Gmail or you have a Google account, it automatically opens this. So, okay, we open this tab, we go to the GitHub option, and now we have like just to go to the Git. We have here. So go to the workshop Git. Go here. If you notice, I included like a new folder here that have the slides. They are all in HTML. You can download it and open in a web browser now with Firefox. But we are not going to use this. We are going to use the notebooks. Okay. You go, copy the address, come back to the Colab, put the address here on this. How is the name of this? Our class, no, like Luneta, Lupa. Oh, yeah, I mean, this searching engine. So you are going, okay, you open any of these notebooks here. Today, it will be this lecture, this notebook. And you'll be able to open run. If you are not installed the GWPy or the FastAI, go to the yesterday lectures, like the first lecture yesterday. At the end, we have like that cells that I said, okay, run these cells on your Google Colab, and it install for you. You just have to run once, and it will be already installed for you every time. Another thing, when you're going to use the GPU, I mean the deep learning stuff, you go to here to environment execution. It's in Portuguese in my side, but I don't know, it will be like another language for you. But you look for this environment execution or environment type on your tab. You go to redefine, or I mean, not redefine, I mean, change the environment execution like this, and you go select GPU. Okay, save. It will reconnect again, and just like make sure that you are connected to the environment, and it will, yes, it's initializing, and okay, we will have. And you see here, you have like some run memory space. You see that's like connected at the GPU backend, and some hard drive space, which is your Google Drive. Okay, and once you have this, you can run my notebooks. I mean, of course, you have like to take care about some paths, because some of these paths, they are defined for my machine, for my local machine. You just need to change the path for the Google Drive. Okay, if you have any questions, just contact me, and I can try to help, and I can try to make things a little bit more easier for you at least. Okay. Any question for now? No. So yeah, we can proceed. I will just like close this and close this one. Okay. I'm also going to show another thing that's really cool. I see my terminal. So okay, let's say we installed everything yesterday with our local machine, and we have like successful all of this, and we have the Jupyter Lab. Okay. See Jupyter. If you type this Jupyter Lab, it will open that environment. It takes a little bit. Yes. It has opened a new here, but I can change it back to it. Right? So Nothing new for now. I mean, we have our sessions and we can have all of this and edit our code, open new notebooks that with the environment that you want, and we can work on this. But we also have another option, which is the Jupyter notebooks as well. Let me shut down the Jupyter Lab. I like more the Jupyter Lab because it has like this quick guide tab here, and I can open like new notebooks or some terminal as a tabs, like as a sub tabs here. Like if I want a new one, I can just like put here, and I'll have like so as a new tabs, like it's like a web browser inside a web browser, like this. But we are not going to use this today because I want to show you something really cool that I use it a lot, and it is to make presentation, make slides. And instead of make slides with the Jupyter Lab, we can make slides with the Jupyter notebook. Okay. You see the environment, the presentation is pretty much the same, but with a little bit of, I mean, it's not like that we have like the tabs and everything, but you can still work on the Jupyter notebook. I think there are lots of people that they prefer to work on Jupyter notebooks and on this interface rather than the Jupyter Lab interface. But why I would prefer this instead of the other one, which I can procrastinate more efficiently. Yes, I would prefer this because of one thing that's really cool. It's called the Rise, and I will show you in a moment that easily convert all of my notebooks notes in slides. Okay, and I can run the cells on the slides. I just need to run this cell here. Today we are going to run some cells inside, and you're going to see how cool it is. So just take this, and okay. So we are good to start. So after this deviation, I mean, we can start with this. Today, as I said before, we are going to at least generate our data set. Is everyone hear me? Is everything okay?
Yes, Filippo.
Yes.
Nice.
Okay,
Yeah.
because it's everyone so silent. I was kind of worried because of this. But anyway, to generate our data sets for our machine learning, we are going to use two libraries, which are the libraries used by the LIGO collaboration, which is the GWPy and the PyCBC. Okay. So you might ask, what is GWPy? GWPy is a package that contains a lot of classes and utilities to provide tools and methods for you for studying the data from gravitational wave detectors for astrophysical or instrumental purpose. I mean, this is really useful. Like in particle physics, we have multicolor generators. We have like the MADGraph, the pt2. We have all of this that we can generate all of this data and analyze this. And also in gravitational waves, why not have as well? In gravitational wave field, we have the GWPy and the PyCBC, which are really great libraries, really good ones, and very intuitive to use as well. I mean, I would dare to say they are way more easy to use rather than root or I mean, what is the JHAP node? What is I mean, whatever. Right? I mean, it's far easier to. I mean, I really like to use GWPy rather than using root. Although PyCBC has some root libraries that I really saw this, which makes me uncomfortable. But okay, they only use the necessary ones. So they only use like it's as a necessary evil, but they use in a very good dose, I think. So for those who knows what the root is, he will understand what I'm saying. So the basic idea for the GWPy is to simplify all the tedious bits of analyzing data allow users to study and plot and quick effectively. For example, GWPy provides an output that you can just like give some input and they automatically provide you like this. Let's say like you give some data series that you generate from gravitational wave, some waveform that you generate theoretically. You can give directly this data series to GWPy and you can like plot the time series like that we are going to see here. Okay, there's some examples. We have like this cell here that I'm going to make this time series and ask to the open data set from LIGO, like from I think that's this server is in here in Europe, I hope, when they go to, otherwise we are going to stay here a little bit while. They are going to fetch this data stream on these timestamps here, these gigantic timestamps. They are in GPS time. So the GPS time, I think they started in 1917, I think so. I'm not sure. And it was like the 0 time, it was this, and since then it can be increased so far. So we have these timestamps, and I'm fetching data from LIGO Hanover and LIGO Livingston. I'm defining here. So let me run this cell. Yes, I think it's I'm not 100% sure.
Interval of 10 plus 10 seconds.
Yes, I think so. I'm not 100% sure, but I think so. The GPS timestamp is secondary. But we can always check this. We have like some data, you put like font type, and it will show you what is the data type for this.
Why did you choose that particular interval?
Because it's a signal that I want to show. Yeah. Yes, there's a signal there. I know that there's a signal there. And we can quickly process here. These are like filters that you can pass through. This is the band pass filters that will cut off frequencies below 50 hertz and frequencies above 250 hertz, like this. These notches, they are like knowing frequencies from noise. They are like knowing noise from this. Maybe Nico can clarify a little bit better about these specific notches that we have on the data. I mean, I'm kind of slack. I should know this, but I'm only using like other people's codes to my purpose. So I usually tend to like, okay, when I really need to know, I'm going asking for this. But usually in the data we impose these notches like this. Do you remember? I know that there is one for the power line noise, and the 60 hertz one I have no idea what it is. Okay.
The 60 hertz would be the power line noise, and the 120 would be like the first harmonic of the power line.
Oh, okay, great. So Osvaldo is working more with this, and he knows even better than me about this kind of notches, and we are building this code together, and we're going to see a little bit more. So we have like this kind of notches that we put on the data and do this. We can run this cell. Yes. I think it was the second one detection. The second detection.
Yeah, I'm curious because you're putting these at 150 hertz, right?
Yes.
But some of the signals will have high frequency.
Yes, but this is like the.
So it's a black hole signal.
It's a merge black hole merge signal. It's like it's very pronounced.
It doesn't move above the 200.
Yes.
Filipa,
Yes?
can you summarize the question for the guys in Zoom, because it was not very clear what was
the question was like if I know what are the signal, like if it was the GW50 or something like this, I don't remember, I don't know, but I have a little confidence about like it was the second detection, and the frequency of signal is not like so high. The frequency is a little bit low because some signals can go above the 250 hertz, and we are cutting off these frequencies like this.
Okay.
So yeah, it's just like a very technical question, but okay. So we're passing this, and we can plot the data. We can think, yeah, if, I mean, can you see here? I mean, I can close and I can show you. Yes, in the notebook.
Is that the signal?
Yes, is that the
So
signal?
that's what you know with the internet.
Yeah. Yes. Yes, it has the timestamp 2015, and I mean, yeah. Okay. And you see the signal from LIGO, Hanover, and LIGO Livingston, like this. We still didn't have like the vehicle yet on this type. And you see, like in few lines of code, of course, like this is just more for plot like this. We fetch the data, we kind of like impose some filterings and something, and we plot like very quickly and very useful. And this is,
Can I ask for a clarification, please?
yes,
I know that for some of the gravitational wave signals, there is a time interval of the level of milliseconds and stuff like this. How do you handle this? I mean, is this already in these, just to make this clarification to so they can follow up a bit?
From these specific signals, they are already handled. This is handled by the sample rate that you can have. You can pass some sample rate, which are like how many times the signal is getting data, like this. We have like different ranges of sample rates. Of course, with more sample rate you have, more data packages that you have, and the more bigger on your memory to fill, like more quickly your memory will fill of this. With lower sample rates, you might miss in some very short bursts like this, but you can scanning more, you can process more data at once like this. You always have like to find this balance of sample rate and memory size. You always have like to do this. One thing that I noticed that people use a lot is just like using a smaller sample rate. Like it's not smaller, like it's sampling every second is sampling 4,000 times per second, like this. And this is okay in terms of memory, but once they get something very interesting, they sample like in a very high sample rate, like 60,000, 24,000 times per second, like this. And with this very small resolution, you can resolve like more details about the ring dial or some funny thing that has happened, like Nico present like this. We have like this post-Newtonian time series stamps like in the region here, like in the beginning, and you have like the numerical, the GR numerical solutions like this, and the perturbative series. And depend on the sample rate that you are going to do this, you can like try to seek out this kind of effects like this. And as I say, we can deal with this with the sample rate and all of this. But this so far, we are getting real data. We are getting like, we're going fetch the data and come back with this. So what is PyCBC? Is again another package that you can do very powerful analysis on this. And you can also generate some time series because we are interested in generating this kind of a series like this. So PyCBC is used by LIGO. There are lots of contributors from this, and it's really good. I mean, if you run things on GWPy, you certainly run things on PyCBC. Okay, and vice versa, you can do. We are going to use PyCBC now for generate our pseudo data. By the means that pseudo is like a simulating, we are simulating lots of merges, generate the waveforms, and to do this, we are going to use PyCBC and some PyCBC functions. But once we got generate the waveforms, we are pass this to GWPy, so GWPy can handle all the preparations for plotting and for selecting everything. Because PyCBC can also do this as well. We can do the whole thing on PyCBC, but I prefer to do with GWPy because it has like more convenient functions and is easier to handle this. Okay. So since we are in speedrun tutorial, We are not going to explore with full details PyCBC, neither GWPy, but I highly recommend you to go on these GitHub tutorials they have. They have the lectures, which are really good. It was there that I learned how to handle this. They have even lectures that like we have like some signal that you unknown masses or unknown thing, and you run some Monte Carlo Markov chain and get some predictions about the chip mass, spins, and all of these other continuous variables that you can infer from the data by itself. But unfortunately, here we don't have time for this. We are in speedrun again, and I will leave to you to your curiosity. Okay. Right now, we are just going to use the things that we need. Okay. So if you are feel adventurous, just go to this Colab, go to these notebooks. You can run on the Colab as the same way that I showed to you, like this, and you can try by yourself. I highly recommend for you to use, just like to give some intuitions. Of course, if you are working on biology cell or something, it doesn't make sense for you to do this. But if you are curious, go ahead and try by yourself. So the thing is, can we build a deep learning model capable of distinguishing between random noise that's generated by quantum fluctuations and everything on the detectors and real possible gravitational wave signals? Can you do this? Can you build this? So short answer, yes. Long answer, we are going to do this on these series lectures. So, but first and foremost, we need data. I mean, machine learning is not voodoo black magic. I mean, we learn things from the data, and to learn things first, we need the data. The good thing is, because since the observation from 2016, the LIGO, they show off all the gravitational wave observation, they are getting more and more events, like every week. I think now with the newest data, it was like, how was the frequency? It was once a week, twice a week. It was something. So we get like lots and lots of data. However, for machine learning, we need way more data, and we need data in a controllable way. Controllable way, that means it's like I generate this waveform from this package simulation that I know for sure that it has like this kind of properties of mass, distribution, spin, position in the sky, because all of these kind of details, they really matter, and they even matter more for the machine learning. Unfortunately, we don't have the technology yet to generate the black holes and gather the data from this. I mean, maybe someday the humanity will be able to do this, if we not destroy ourselves before, but okay. But we have computer machines. We have computers, and really powerful ones. I mean, right now is a really good, is kind of like a golden age of computer simulations and computer machine, because not long ago, to generate to run some Monte Carlo simulation in these things, you have to have an account on a high power computer like a HPC or some cluster of some sort. And we can do this on laptops today. I mean, this is like, it's not like very long time ago, and we can do this. Of course, it will be a little bit slower than if you run in a HPC, but you still can do some really cool analysis, really cool job on your laptop, on your desktop as well. Okay? Yes.
Just to make it clear in my head. So you say we need a lot of, unfortunately, we still don't have access. No, sorry.
Yeah.
However, we need a lot of data. No, it was there. To train, yes, we need a lot of data to properly train our models. But so to clarify, I was under the impression that you train the models with synthetic waveforms.
Yes.
From the simulation. Right? Yes. So you really don't need data to train the models. You need the synthetic simulation.
Yes.
And then you apply the data, right?
Exactly.
Right.
Exactly.
Okay.
I need like to consider all possible kinds of parameters that can interfere on the wave. I mean, I can consider this, and I can just shove this on the machine learning, and the machine learning will try to figure out.
Right.
I mean, it's not my problem. My problem yet is to generate the data. This is like my first problem. So And yes, we only need to generate synthetic data. We don't need like real data.
Not real data.
Yes.
Exactly.
I mean, it would be great if you could generate real data. Like as I say, like have like generate black holes. I mean, it would be really, really great.
There are analog black holes.
Yeah, I know they are analog, but you need like a swimming pool to do that. Can we apply for a grant for this?
Maybe.
Maybe we can apply. Let's do this. I mean, I would be really, really, really happy to work on analog black hole with image data. I really wish to work on this because I have like really crazy ideas to do. But yes, that might be something to consider. That might be something like to keep in mind. Yes, but we have computers. We also have quite smart people to do this job of simulating this, aka grad students and postdocs here. So, and we just need to bring this together and try to solve this problem. Okay, so I think that's better for me to continue on like this because it's not showing. Okay, so first step is like what kind of data that we want to work like this. This is like every time when someone comes to me, that's like, oh, I have a really good idea to work on machine learning, but I don't know how to do this. And I say like, okay, first thing first, the thing that I have to spend more of the time is the data itself. What kind of the data are you going to work? Are you going to work with images? Are you going to work with text? Are you going to work with time series? Depending on the way the data that you are going to work, this will modify your machine learning by itself. Okay, we can, in the case of gravitational waves, which is really, really rich case to work on this, we can work with images. Here, an example that some images, these are generated from the Q transforms for the waveform that do this. This is like a frequency on the vertical axis over time period. And the colors here are the signal, the frequency strength of the signal. Right? So here we have like this kind of ghostly image like this. This is a combination that was Osvaldo's idea to do this, to combine the signals from 3 different detectors in one image and associated this each one of these detectors as a color channel, let's say. Osvaldo, do you remember the order? It was like a blue, Virgo, green.
Yeah, green's Livingston and red's Hanford.
Yes, okay. So we set this. Why, you might ask? Because most of the computer vision, the convolutional neural networks, they are tailored with color images. But you can like say, okay, if I have a new detector, if I have Kaga, if I have like or Lisa in the future, can we still work with this? Yes, you can, because this machine, they're not limited by the dimensions, like only 3 dimensions. We can put like another vector and you'll be like a 4th dimension. And you put like a new data, it'll be a 50th. Yes.
Next question. So the pitch of the time series has different time axes.
Yes.
So how do you decide the shift?
Yes, I'm going to show this as well, because in GWPy they have a very convenient functions that you can, not GWPy, is in a NumPy function, that you can find the peak on the time series to find this, and you define a window on this, and you can like try to find because of course the gravitation, the wave will pass through the detectors, and the detectors they are far apart from each other, like this. And we are not in a flat Earth, okay? We are like, it's rounded, okay? I mean, it's a constant, yeah, it's rounded, no question. And since it's moving in the speed of light, okay, we tested this, it's like 10 to the minus 15, the difference like this. So as you're moving the speed of light, the gravitational will pass in different times. And we have here, as Carlos pointed out, we have different time this. And we have to take this shift accounts. And we can do this as well. We can find like the different shift time from this, and we can bring it all together, combine, and stacking the images. This is one thing that you have to take care. Another thing is because also you can just don't take care about the time difference, the time split difference, and just put the images, just stack the image as it is. By doing this, it's really interesting because some models of machine learning can learn these features, this different, because we have like kind of different peaks regions in different time. And the convolutional neural networks, they're really, really good to learn this kind of translation invariance properties. And she kind of like, it's not a wishful thing, but if you build the model in a way, try to figure out the difference time on this, the machine can figure out this difference between the peaks and make the computation from like, okay, this signal passed first on this, second on this detector, and third on this detector. And by this triangulation, we can locate the position of the wave on the sky. We can build also this kind of models as well. I mean, of course, it's a little bit trickier. It's not like direct like this. You have like to be really, really thoughtful about this. But still, you can try to like use this in our advantage as well. Okay. Another kind of data that we can use is the time series by itself. It's like the signal strength. The time series, it will show like this. It will show a NumPy array with numbers, and we can use this. We can build some models that can leverage this kind of signal, a time signal series. One of these models of machine learning that we can use this time series, they're called the recurrent neural networks, which are really interesting models, are the same models that you are using for your phone translator. When you're using Google Translator or any translator at all, these are recurrent neural networks. These are like this kind of a neural network. Because why, you might ask like this, why is it interesting to use this? Because as I'm speaking to you right now, I'm trying to figure out the best way like to translate in my head from Portuguese to English, and I try to do this. And we know that language has a time stamp like this. You have like the words, you have all the pronouns of the words. Like if you pronounce completely random, it will not make sense. So one step depends from another. It's a time series like this. That's what I'm trying to say. And these language models are ideal for this kind of time, because in here, if you remember, like this time series here, like if you see here, it's kind of like each step of second depends from the previous one. It was like this, and it grows. You can build machine learning models that learn this kind of features, that try like, you can build like a machine that goes like, okay, the signals start a little bit funny. Maybe something will happen in the next 5 seconds. And these things can be a gravitational wave signals. And you can build machine learning models that can flag these kind of things, that flag and anticipate for you, okay, turn on the detector right now because it will come some signal really, really nice, really strong. And if you can even like, if you have like more sensitivity and more, I think with the LISA, with the space base, we might be able to get these kind of signals from fainter sources, like binary neutron stars, because we have like a very, very long signal and they're like very, very faint. And for Earth detectors, this is kind of really hard to predict. But for space-based, we can predict this. And we can say like, okay, we are get some signal from this region on the space, point the telescope for there, and we get the gamma ray burst, we get the electromagnetic counterpart like this. Or you can even get some other information like from, I think there are people trying to use gravitational wave information from collapse of very big stars. Like this, try to predict when some gigantic star will collapse and will become supernova, and you can kind of get like try to do this. And yes, if you have the data, if you have the detector sensitive enough, if you can mount this, you can build a machine that's like, okay, based on this behavior, I know that something might happen with 99% of confidence level. And this is another kind of data treatment that we can use like this. And the other one, which is really interesting, and I hope I have sound here and people on the chat can listen, is to work with, convert this time series here on audio, like audio waves, say, and you can listen to this, okay? You guys heard on the
Yeah, yeah, we did.
Yeah.
It's
so
kind
yes,
of a wind or something like this.
yes, I can play again. I can show
Okay.
off. Okay, which is really nice. I mean, this is like a pure wave. This is like this, and this kind of data set that we are experimenting with Onofre and Osvaldo as well as a new source of information for detecting not only gravitational waves, but also trying to cleaning the signal noise. My last lecture, I will show off some of the techniques to cleaning noise from the signal data, and they are really good. They're really amazing. I think that's a really good opportunity, and has a lot of things that we can work on this with this kind of different types of data set. So just one more time. Yeah, this is really cool, and this audio sample was generated with using GWPy as well. They have like, I think that was PyCBC. Yes, I think they have like an option that you can take the time series and just like export as a wave like this. Of course, be careful, especially with the sample rate, because if you generate signals with a very high sample rate, you feel very easy your hard drive like this, because if you put like a sample rate of like a 24,000 hertz or something like this, each file will be about 2.5 gigabytes. And if you generate 5,000 files, you get like a little bit of over 1 terabyte. I mean, you can generate if you have a machine for this. I don't. You can do whatever you want, but yes, I mean, be careful. Okay. For simplicity of this, we are going to work on images. Okay. Okay. So to generate the images, we are going to import all of these packages, all of these libraries here. I can go for some of these because later we are going to not only generate the waveform, but we're going to pass this waveform to the detector, because each one of the detector has some proper characteristics on this. I have 50 minutes, right? Okay. We are going to continue on this on the afternoon session. So we are going to, again, but it will be just the extension from here. I'm doing this because I want people keep it on the afternoon sessions. I want people like to learn more about it, okay? But yes, one thing that's really cool, and me and Osvaldo use it a lot, is this spool thing. This spool thing is a really nice class from Python that you can distribute all your workloads in your threads, in your computer threads. If you have like a computer with 80 cores and 16 threads, you can just put all the threads to run it, and it will be faster to be like this. If you have like 64 threads, go on, it to be even more faster. Like PyCBC is able to use GPU acceleration, but you have to be a little bit more careful about CUDA. You have a little bit more knowledge about CUDA. And I can tell you, CUDA is not a so friendly language to learn as beginner. But if you feel adventurous, go on. I mean, nothing's holding you, so just go on. This TQDM here is a library from Python that just show the progress that they're going to do. I like to do this because I don't like to give scripts to the machine and don't know what they are doing. So this TQDM shows me the progress that we are going to use. And this OS and Sys is just like the OS library just to create folders, anything that we need. Okay. And also these warnings here is because Python is kind of like really, really annoying for some things, like especially with older libraries. And I have a tendency, like if I know if the code is running right, I just like, okay, just ignore the warnings and just don't bother me at all. But I would only say that's like only put this after you know your code is running and they are doing the things that you want to do. Okay, let's import here. And another thing that we're going to use, and is important as well, it is the noise. Okay, let me just take a bit of water. Why noise is important? Because with PyCBC, we generate the waveform pure, like this, from mathematical. We have like the textbook example. We have like the the mathematical stuff, the really neat thing. But it has a huge difference from the textbook examples to the reality, okay? And we don't want our machine to get addicted to the textbook things. We want our machine to get addicted to at least know what is the reality. So the noise, it is kind of like this kind of stronghold that you will know that you are going to have at least something that is plausible on reality like this. So this noise, it will be the thing that we are going to use as a baseline. Let's do this. First, to generate like our noisy classes, our noise examples, like this, the pure noise. And secondly, to make our signal, to make our data as close as possible to the reality. So in a way that the machine will try like to consider as well this kind of thing.
So is this real noise or a model?
This is real noise. This is noise from the detector.
There is a signal in this noise?
No, I think that they're clear. They say that I don't have any signal on this noise. They have like this is just a channel for noises.
Philippe,
Okay.
can you repeat the question for the
Yeah.
audience?
Carlos asked is like if this like some Gaussian noise or some synthetic noise, or this is like a real detector noise. No, these are like from LIGO. They turn on the detector, but in a way that's not like detecting gravitational waves. They have like this kind of a two switch for this, and only like to collect the noise. And this is data from this kind of event detection, like not event detection, but it's like noisy generating detection like this.
So Philippe,
Yeah.
Just in general terms, what you do is that you know what is the time window that you have this signal, and you move away from that in order to pick up the noise.
Yeah.
Okay.
I mean, you can also generate some Gaussian noise as well. You can also generate this synthetic noise. But yes, of course, it would be a Gaussian noise. It would be like this. But the thing is, these machines, they are so sensitive, they even can learn what is a Gaussian noise. I can even like build a data set that is a Gaussian noise and that is a detector noise. And we can even classify this with a very good accuracy. So even these kind of things, they are sensitive. That's why I always tell to people, like, really think about your data. Really think about your data, because the things that you're going to do, these machines, they are lazy as it can get. I mean, this is not like a thing. So you have always to take care about this. You always have like to see what they are doing and see and try to think about the machines that are doing. Okay.
Yeah, and I can see that for each detector, you're importing noise.
Yeah.
And you're importing 3 different time series.
Yes,
right?
exactly.
So why 3? So is there a kind of choice of samples of noise that the collaboration itself provides, or why these 3 time series? Or you understand my question?
Yes, I understand. Why these 3? To impose even more randomness on my data. Like first, because we have like this. And second, I explained just below, we have two sample rates. We have like one really big sample rate, like 60,384 hertz, and we have like a smaller ones. And each one for the detector, like 3 for each detector, because this one, they are collecting different times stamp. So they are not only random on the time itself, but they are random on each sample itself. And when I'm going to build my model to generate the images, I impose some random selection on just like, okay, based on this number, on this random number that I generate every time, collect one of these. Like try to make as random as possible. Not only collect only one noise, but try to collect the noises in different regions and different paths. Like try to really simulate the randomness on the detectors. I'm trying to do this. Yes, to increase, yes, exactly. To even like not only make difficult for my machine to do this, but also take into account these detectors, they have like this intrinsic randomness on this. And this is why I'm getting like this. I mean, you can even put more and more, put like a 80 time series or 80 things, or like even build your time series that you fuse together. You can build really crazy stuff. Try to say to do. And okay, it was me. No, yeah. So we have this. We have the noise. I even have like a folder in my data that I call it a lot noise. I have like to share to you guys the noise if you want to run the code. I will share. Another thing is I completely forgot about. Have you guys received the email with the link to download the data I generate? It was generated with this code. And have you guys tried to download it? It's working. It's failing. No? Okay.
We got the link yesterday. Yes, I think it was Alexander that sent it with.
Yes.
Yeah.
I download them. They are okay.
Okay. Great. So at least they're working. Okay, great. I was a bit worried. I will send another link if you want the noises, or Osvaldo can send to me the link. He downloaded this noise and I can send to you. I can forward to you guys. So okay. You see here this folder super resolution. This is another project that we are using, and it's funny, but yes, we are going to load these noises, and as you can see, we have these different kind of things. Okay. Here I define some paths that are to generate the folders that are going to use the noise. I mean the images they're going to save. But no worries. I mean, there's no need to worry right now with this. This is just things that I usually set up to save the images or save some models or something. And no need to worry about to check this. So we are going to use from the PyCBC this class here, like this get time independent waveform. It also has another class that's called get frequency dependent. This get it's not beta phi. It's not running. Have I imported? I think I did not. Yeah. I think it's not auto-completing. No. But again, waveform. No? Okay. I think that's because it's not imported. Okay. Yes, I only ported get TD, and I did not port it get FD. Yes, you see, now you have like this frequency dependent waveform as well. Okay. But for today, we are just going to use the time dependent. Okay. It's not really big deal. You can use one or other, it doesn't matter. We are using the time dependent because we are working on the time series dependence, and it is easier to do as this way. And as you can see, you can just like put the, as I said before, like you can put the question mark, and you get like this message here, and this message is the patterns that you can feed into the function by itself. And you can see like you have like the mass of the objects, the spins, lambda. This is like the dimensionless, tidal, the formability, and you have all of these really crazy parameters. You can go really deeper on this. And this doc string, you can like explore each one of these parameters, and you can go off this. We are going just to use some few parameters as example for you. And I'm putting here like the approximate it is the function that generates the waveform for you, because it has like a collection of functions that you can check on the PyCBC documentation. Each one has some specific characteristics that deals with spinless black holes or with spins. Maybe you can clarify a little bit more about the approximates and a little bit. I mean, I'm using this because I saw a lot of papers that people are using this, but you can use all the other ones. Yeah, you can have a show on these files. Like, you go to the documentation, you can have like a list of all of these approximates, and you can even build your own approximate and put on the library. Like you have like they have a tutorial to do this. You build your own approximate, put in the library, and you can run you can generate your waveforms with your own approximate as of this. And we can pass some basic parameters for mass and the time, the delta t, like, or the duration of the noise, and some distance. Here, the distance are in megaparsecs, like this. The unit are in megaparsecs. So I'm passing, like, I'm trying to simulate the waveform from a black hole mesh with 20 and 25 solar masses at 600 megaparsecs with inclination at 90 degrees, like this. So, yes?
Just to be clear, so how is this generating the approximate waveform? So does it have a library?
Yes.
All numerical relativity waveforms and then it kind of interpolates?
Yes, exactly. It goes, yes, exactly. They have like a collection of all of these approximates. This approximate in specific is for time domain series of this, because we have approximate for time domains and for frequency domains. This one we have like for time domain, and it is interpolated. This they have like they have this constant updating library of approximates and numerical simulations of this, and we are just using one of their numerical approximates to generate our waveform. In my case, I'm generating the polarization. They always return the plus polarization and the cross polarization, the plus and cross. That was like this.
Yeah, fully understand. So you're not putting spin or?
No, I'm not putting spin here in that case.
And the inclination is the inclination of the orbital angular momentum, or what does it mean?
Yes, we can. We can check here. Mass, spin, insert lambda, for inclination. Inclination defined as the angle between the total angular momentum
and the line of sight.
Yes.
So that means that you would be edge on.
Yes.
Case, right? So
exactly.
Like this, right?
Yes, exactly. Okay.
Felipe, maybe you can summarize the discussion to the guys on Zoom?
Yes, we are rich at the time. Unfortunately, we are going in this afternoon. We are going to pick up from here, okay? And luckily today we will finish the code to generate the data. So far, we are just putting our toes on the water and to generate this. Okay?
Okay. So Philippe, your suggestion is that we close the lecture now, and probably if there aren't any questions, this is the right time to put them before we go for lunch. Okay, I don't see any. There is one.
Miguel,
Miguel?
raise the hand.
Yeah. Are you listening to me?
Yes, Miguel, go ahead, please.
Okay, I have a little question about the final frequency in the get_td waveform function. Why are you using this frequency? I don't know what is the value for this frequency.
Yes, you can pass this information as a cutoff frequency like this, because you have like from the waveform that are going to generate like this, some of this information, the two most important information to be like the final frequency of like this, of the sample rate, and the duration like this. You have like always to pass this, because otherwise it will be not, they will not know how to generate the size of the shape. Like you see here, you have like this shape. This shape are dependent on this final frequency and the delta t. Like this. You always have to pass at least some values like this. And I'm passing the values, like this final frequency, from the sample rate values of the noise, like this. This is kind of like I'm passing some information to not generate all of these. Let me go back to a little bit up. It's not here. Oh, I mean, I will give you some spoiler for this afternoon. But here, you see?
Yep.
These two parameters, this the final frequency, it will like give you the size of this waveform like this. If I don't pass this, like if I don't pass none, it tends like to generate this infinity. Like it will continue from here to infinity. So it will fill up your memory and it will become slower and slower like this. Or it will give you a message that he doesn't know when to cut off. So you have like to give this kind of cutoff.
But the thing is, why do you know this value for the final frequency is, for example, after the merging phase? I mean, in order to capture all the merging.
Why this value? I mean, I don't understand clearly what.
I mean, why do you know that this value for the final frequency?
Oh, I don't know. I'm just give it to them, and he will generate the waveform with this constraint like this.
Okay. I understand. Okay.
It's not because I know and I have like a superpower. No, this is just like a giving the number, and he will have to deal with this kind of thing.
Okay, I understand. Okay, thank you so much.
Yes, Carlos.
As a related question, so whereas the lower frequency is fixed to be 20,
yeah,
the final one depends on the noise. You could have just fixed it to be 1,000, say.
Yes.
So what's the advantage?
The main advantage, I'll give the advantage for the computational.
Hang on. Can you just repeat the question?
Yeah, so the question was, whereas the lower frequency was fixed at 20 hertz, the final one depends on the noise. So I asked, why not fix it as well, say at 1,000 hertz? So what's the advantage of doing it in this way?
I would say the advantage by doing this way from the computational part, memory. If you have a computer that has a lot of memory that can handle this, put like 10,000 hertz, why not? But if you are constrained to run your laptop, put some things that make a little bit more sensible for you. I mean, the only constraint is this. The only constraint is your machine. I mean, people say that like to say, "Oh, your only constraint is your imagination." No, the only constraint is your computer. Okay, and your money by extent. Okay? If you buy a Ryzen 5 or some like an Epic ROM and with 20 terabytes of memory, you can put whatever crazy stuff that you have in mind. But since I'm thinking more about not like the low end of the bell shape of computer, but like the middle, like the 1 sigma on the bell shape of people like this. And yes, that's it. But it has many other parameters. You can play a lot of this, and you can see this difference on the waveforms. You can try. That's one thing that I would suggest for you for after the afternoon session. It will be like, try crazy numbers on here, try different numbers, try things like, try to break the code. I mean, try to do this. The worst thing that will happen to you, it will give you an error message. The best thing, it will give you some very interesting signal for you. This is here to play, that's right. Okay?
Okay.
Yes, this afternoon we will continue from here, and we'll take from there. Okay?
Okay, I think I don't see any question in Zoom, and probably not in the room as well. So I don't know, Carlos, we could close the session and reconvene at 2 o'clock.
Yeah, I think let's do that. So let's close it for now, and we'll resume at 2.
Okay. Carlos, Antonio is picking up the chairing the afternoon session just like yesterday?
Yes, I believe he's willing to do it, so he will do it, yes.
Okay, thank you very much. Okay, see you in a minute, guys. Thank you very much.
Okay, bye-bye.
Bye.
Carlos, I have sent you a message.
Yes, I noticed. So I'll do my best to actually make the lectures available, okay?
You know, this is whenever we are successful, that's the type of reaction that people have, you know.
It's a good sign, I would say, yes.
Good sign, yeah. Okay. Bye-bye, everyone. See you
Perfect.
later.
Yeah, talk to you later. Bye-bye.
Thank you.
Okay, so yeah, I feel like going and playing with the way for
Yeah, I mean, it's really fun. It's really, really fun.